Hitesh Mittal, a student of Chitkara University, Punjab. Today, I will demonstrate to you an experiment which I have designed using analog ICs from Texas Instruments. The ICs used in this experiment are temperature sensor LM35CAZ. I have used two of them in this experiment. General purpose operational amplifier TL082. Each of these ICs has two op-amps and I need 4 of them in this experiment. Quad 2 input NAND gates CD4011BE. I am also using resistors and 2 potentiometers and 2 indicator LEDs. My experiment deals with sensing the temperatures from 2 different sources and alerting the user through 2 indicator LEDs. 2 temperature sensors sense the temperatures T1 and T2 and compare them to reference values θ1 and θ2. The specification of the experiment is if T1 exceeds θ1, then red LED indicator must glow. If T1 is lower than θ1 and T2 exceeds θ2, then green LED indicator must glow. Only one of the two LEDs will glow at any time and T1 takes priority over T2. Here is the design for this specification. I first measured and calibrated the temperature sensors. It turns out that for every degree centigrade increase, the output increases by 0.01 volt. The output of each sensor is amplified with a gain of approximately 20. As you can see, there are two identical circuits associated with each temperature sensor. The output of sensor is fed to a non-inverting amplifier. The output of this amplifier is fed to another non-inverting amplifier but with a reference voltage. Let us zoom in on the second stage of the amplifier to understand it a little better. There are two inputs to this amplifier stage. One is the reference voltage Vref connecting to the inverting terminal. The input connected to the non-inverting terminal is coming from the first stage amplifier. We call it Vin. Analyzing this circuit using superposition theorem, we see that output voltage Vout is given by this simple formula. In our implementation, we use a reference voltage of 0 and formula simplified further. We can see that the output Vout is same as Vin. Let us go back to the original slide. I have labeled the outputs of second stages as A and B respectively. The combinational circuit which implements the priority logic is implemented using NAND gates. It can be simplified as shown in the diagram. The first output simplifies to A bar B. The second output simplifies to A. In other words, as long as the temperature 1 exceeds the threshold, the red LED will glow. The blue LED will glow if temperature 1 has not exceeded the threshold and temperature 2 has exceeded the threshold value. Notice that A is the output of an analog circuit and is being directly fed to a digital circuit. Here I have plotted the output voltage A as a function of temperature T. In our NAND gate, which is operated with a VCC equals to 10 volt, a voltage of 7 volt or higher is treated as logic 1. I have adjusted the output A at temperature θ1 to be slightly higher than 7 volt. Similarly, I have adjusted output B at temperature θ2 to be above 7 volt. In other words, I am able to directly connect the output of analog circuit to a digital circuit. Coming to the demonstration, here a dual supply operating plus minus 10 volt is being used. Initial temperature is same as room temperature, which is nearly 20 degrees Celsius, and LM35 is showing 0.205. The reference is set to 35 degrees Celsius. For testing, I am using heat through a power dissipation of 3.3 ohms 2 watts rated resistance operating on 0.8 volts 0.5 watt power supply. The digital thermometer shows 104.3 Fahrenheit or 39 degrees Celsius. The temperature sensor LM35 is showing 0.394 volt. If resistance is touched with temperature sensor T1, then according to the logic, red LED is glowing. With temperature sensor T2 but with temperature sensor T1 less than reference, then LEDs glows. See what we can learn from this experiment. When output A becomes close to 7 volt, which is recognized as logic 1, the output of the gate is somewhat uncertain. There is a voltage range of 7 volt plus minus delta where A may be treated as logic 1 or logic 0. The same goes for logic B. What happens when temperature increases beyond theta 1 or theta 2? The analog voltages A and B can exceed 7 volt. Since we are operating the op-amp stage with the VCC of plus 10 volt, we are ensuring that A or B does not exceed 10 volt. As a matter of fact, they will not exceed about 9.2 volt. Conclusions: while trying to directly interface an analog output to a digital circuit, there can be a voltage range where the digital circuit can be uncertain about the logic state of the input. I will be happy to get your feedback. Please provide your comments on this YouTube video. I got all the ICs used in this experiment free from TI. You can also try the free samples program by visiting www.ti.com. I also took part in TI's Innovation Challenge India Analog Design Contest last year. You can also take part by visiting this website. Thank you.